Hi, my name is Hayston Saylor. Today I'm going to be talking about the problem of a complete coloring in graph theory and finding the achromatic number for a graph. And I'm going to be tackling this problem using the approach of a genetic algorithm utilizing the wisdoms of crowds. So first I'll need to define what exactly a complete coloring and an achromatic number are for a graph. And to define those terms, I need to define a vertex coloring. So a vertex coloring is simply a way of coloring a graph such that no connected vertices have the same color. An example of a valid vertex coloring is shown on the right on a Peterson graph. I pulled that image from the Wikipedia page for graph coloring. So then a complete coloring is a vertex coloring. It has the same requirements as a vertex coloring, but it also has the requirement that every possible pair of colors for the number of colors being used must appear on at least one set of vertices. So then the achromatic number is the maximum number of colors that can be used to produce a complete coloring for a certain graph. An example of this is shown on the right on the Klebsch graph. A complete coloring of it is shown with 8 colors, and coincidentally, the achromatic number for that graph is also 8. So now that the problem has been defined, I want to take a second to talk about the basic setup of the genetic algorithm being used. So individuals for this problem are represented as a list, and the indices of that list are vertices in the graph, and the values for each index represents the color of that vertex. Um, each individual has two fitness values, and these measure conflicts with the previously mentioned requirements for a complete coloring. One of these calculates how many connected vertices have the same color, which is in conflict with the requirements for a valid vertex coloring. And then the other measures how many pairs of colors aren't represented in the graph, which is the second requirement for a complete coloring. The mutation operator I used was just a random recoloring. So a random number of vertices are recolored with a random color each time that an individual is mutated. For crossover, I used PMX crossover, which stands for partially mapped crossover, and I modified the normal PMX algorithm to copy pieces of the solution from both parents based on neighbor relationships in the graph, rather than how PMX normally bases it, which worked well for TSP, but not for this problem. And then finally, with missing colors, after any mutation or crossover, individuals are checked, and if they are missing any of the possible colors, they're edited to reinsert those colors. And this is just to make sure that every individual is valid for that number of colors. And so no individuals in the population are wasted testing for a lower number of colors than we need to be testing for. So now that I've talked a little bit about the basic setup of the genetic algorithm, I want to take a second to talk about how I integrated the wisdom of crowds into it. So first, the wisdom of crowds is simply the process of identifying patterns in well-performing individuals of the population, and then combining those patterns to produce a new solution. So the way my wisdom of crowds works is it grabs the most commonly occurring vertex color pairings in the top 10% individuals of the population. And by vertex color pairings, I mean, say vertex 7 is colored red in every one of those individuals. It would be picked as one of those common vertex color pairings, vertex 7 colored red. So the number of pairings obtained is equal to 20% of the total vertices in the graph. And all of these vertices have to be unique. We don't want any redundant vertices. So then to combine the solution, these commonly occurring pairings are simply placed into a new individual. And then the vertices that are not specified in that list of pairings are refilled using a simple greedy coloring heuristic. And then to integrate that new solution back into the population, enough copies are made to replace 10% of the population, and then those copies are put through a chance of mutation before being added back. This is to add a little bit of diversity so that the same individual isn't copied and added back, replacing 10% of the population. It preserves diversity. So now that I've talked a little bit about how the different pieces of the genetic algorithm are set up, I want to talk a little bit about how the overall structure of the evolution of the population is set up. So first, the initial population is created, and it searches for a complete coloring at 3 colors, and then the evolution loop is entered after that population is initialized. So first in the evolution loop, wisdom of crowds is performed. And after that output is added back, replacing 10% of the population as discussed before, the rest of the new population is filled using the normal genetic algorithm methods of mutation and crossover that I discussed a couple slides back. And then after the population is filled up, the best solution is grabbed, and it's saved to the improvement curve along with some other relevant information, and then sent to the GUI. But the best solution is only sent to the GUI and updated every 10 generations, and we'll talk a little bit more about that later. And after the final generation, the improvement curve is graphed. Colors are increased only under certain circumstances. So there's one of two situations where that would occur. The first situation is just anytime a complete coloring is found, because once a complete coloring is found, that means that the achromatic number is at least that number of colors. So we want to increment and test for the next higher number of colors. The other situation is if a complete coloring has not been found yet for any number of colors, we don't want to spend too many generations searching on one number of colors. So every few generations without improvement on one certain number of colors, the number of colors is incremented if a complete coloring hasn't been found. And this is to prevent stagnancy of the algorithm. This does cause some issues to arise, and those will be discussed a little bit more later after our results. So now that the information about the algorithm itself is out of the way, I want to talk a little bit about the GUI. To open your test file, there is a dialog that will take you to your file explorer where you can then find your test file. Once that's opened, the GUI initially plots the graph with no coloring information, and this shows up as a graph with all vertices colored red. After that, the results are updated every 10 generations, with the update including runtime, minimum achromatic number, if a complete coloring has been found. If one has not been found, that is labeled as NA. It also shows the number of conflicts in the current graph for that generation and the number of colors. And then at the end of the last generation, the improvement curve is plotted, and you can see that in the example on the right at the bottom. It's a plot of the number of conflicts in the current graph versus the generation. As you can see, it is also separated by vertical lines, and the sections created by those lines indicate the number of colors being tested during those sections. The color of the sections themselves indicate whether a complete coloring was found for that section or not. Red indicates no complete coloring, green indicates that there was a complete coloring. Another note is that the final graph shown by the GUI will not be a valid complete coloring, and that's because the GUI is still searching for a complete coloring for that number of colors, so the final graph plotted won't be valid. So before I talk about the results of testing, I want to take a second to talk about the test data and how it was generated, and then a little bit about how the tests are conducted. So the input file format is shown in that little example there. It's just a text file with the vertices and edges listed under headings. And then I used 5 different graphs in the testing. The first being the Klebsch graph, which I found out about on the Complete Coloring Wikipedia page. It is a 5 regular graph with 16 vertices. The reason I chose it is because it has a known achromatic number, and I could basically benchmark the algorithm with it, make sure it was working okay. And then after that, I generated my own graphs, 4 more, using simple Python scripts. So I generated 2 random graphs, one with 50 vertices and 500 edges, one with 150 vertices and 3,000 edges, and then 2 regular graphs, one 20 regular with 100 vertices, and the other 30 regular with 200 vertices. Um, and so each graph is going to be tested with varying crossover and mutation rates in the genetic algorithm. And for each variation, data was collected from 10 different runs and then aggregated into performance statistics, which I'll show in tables. I also want to note that uh, for some of the graphs, I varied the amount of generations, and I'll talk about that when I get to those graphs. Also, a population size of 100 was used for all of these graphs. And so the first set of tests I'll talk about is the Klebsch graph. As mentioned before, I use this to benchmark the algorithm. Um, the algorithm with 75% crossover rate and 75% mutation rate was both the most consistent with the lowest standard deviation, and it had the best average performance. But all of these algorithms performed fairly well on this graph. They all were able to find the known optimal solution. And I think that was because this was such a small graph. It seemed to be very trivial to solve for the algorithm, being as it was able to find the optimal solution in only 50 generations. So next I'm going to talk about the results of testing on the randomly generated graph with 50 vertices and 500 edges. I want to make a note here that for these 2 randomly generated graphs, I did make the requirement in the script that I wrote that all vertices generated must have at least one edge connected to them. That way there's no floating vertices. So the best performance on this graph was again with the 75% crossover, 75% mutation rate algorithm. But the most consistent this time was actually the 25% algorithm. Uh, the optimal solution for all of these graphs that I generated is unknown. But for this one, both of the 75% mutation rate algorithms found a maximum best of 15. Um, the biggest note that I had here was the algorithm noticeably benefited from higher mutation rates on this graph specifically. So next I'll talk about performance on the randomly generated graph with 150 vertices and 3,000 edges. The best performing algorithm was the one with 75% crossover rate and 75% mutation rate. It was also the most consistent and found the best solution. The optimal solution is unknown, but that algorithm found a maximum best of 22. And with the first occurrence of failed runs, which will be discussed more later, occurring on this graph, it was the only algorithm with no failed runs occurring on it out of the 10 runs. I also want to note that I ran this graph for 150 generations. Next, we'll talk about the performance on the 20 regular graph with 100 vertices. I ran algorithms on this graph for 100 generations, and the best performing one was, again, the 75% crossover rate, 75% mutation rate algorithm. It was also the most consistent, and the optimal solution for this graph is, again, unknown, but all variations were able to find the same maximum best of 17. The final graph we'll talk about performance statistics for is the 30 regular graph with 200 vertices. On this graph, I ran algorithms for 150 generations. The best performing one was the one with a 25% crossover rate and 75% mutation rate. The most consistent was still the 75% crossover rate, 75% mutation rate one, and it did still find the maximum best solution of 26, although the optimal solution is again unknown. But it seemed that variations with a higher crossover rate performed worse on this algorithm than the ones with the lower crossover rate, and failed runs occurred more often all around. So next I'm going to talk a little bit about the failed runs mentioned in previous slides. So a failed run is just a run that couldn't find any complete coloring for any color that it tested. An example of that is shown on the right, where every single section of the improvement curve is colored red. Common reasons for this are that too many colors were needed for the complete coloring, and that many colors wasn't able to be reached in the amount of generations given for the algorithm. Or the solution space could have been too large and it wasn't explored fast enough, and the number of colors that could have created a complete coloring were passed up before that complete coloring was found. Possible fixes for this are that larger graphs could be ran for more generations or with a larger population to explore more of the solution space. But the main trade-off with this is that it would inflate the runtime by a large amount. But both fixes, either by increasing the number of generations or the population. So to conclude here, I've aggregated all the data from the previous tables into these two bar graphs for the average achromatic number found and the average runtime for the different algorithms on the different graphs. Notably, the best performing graph, or the best performing algorithm across multiple of the graphs seems to be the 75% crossover rate and 75% mutation rate algorithm. The only graph for which this wasn't the case was the 30 regular 200 vertex graph. But I think with a higher population size, it may have performed better. Additionally, runtime seemed to be proportional to the number of edges in the graph, not the number of vertices. Finally, this last slide shows some of my references I used for this project. Notably, one reference is on here that isn't in my references in my report for this project, and that is the reference to the Wikipedia page about graph coloring. I included that on this presentation because I got the example image of a vertex coloring from that page. Thank you for your time, and this concludes the presentation.